with the USDA Forest Service, stationed in Corvallis, Oregon. I've been a research hydrologist with the Forest Service since mastodons walked the earth, and will probably spend my entire career in one office. But it's been a great gig, and basically, my work is kind of at the intersection of geology, hydrology, and what, it sounds like a big falutin word, geomorphology, which is basically the study of processes and landscapes at the surface of the earth. And I sort of work in that stew of issues. And I've worked on all kinds of things. I've worked on the effects of dams, putting dams in rivers, taking dams off rivers. I think the Forest Service hired me originally because I was interested in consequences of cutting trees on rivers. Does the river know that it's been logged? But then I've sort of also worked on the effects of volcanic eruptions on rivers, effects of rivers on volcanoes, and more recently, the effects of climate change and such on rivers, glaciers, and things like that. So I've had this pretty broad buffet of issues that I've been working on one form or another. But my home waters, and the most consistent theme throughout my entire career has been the McKenzie River. And I didn't start, saying, well, I'm going to be an expert on the McKenzie River. And I don't think I am an expert on the McKenzie River. I just have spent a lot of time thinking, studying it, and just meditating on it and so forth. And so what I thought I'd do today is just sort of give some perspective from largely drawing from the work that my colleagues and I have done on this river, to convince you, if you're not already convinced, that the McKenzie River is one of the most unique and special rivers in the world. Therefore, by extension, the universe. By the way, how many of you have ever heard me talk before? Just a simple show of hands. Oh, okay. My wife did not raise her hand. I don't understand. So, if you have heard me before, some of this will probably be, if not old hat, at least a repeat review. But there's hopefully some new stuff in here too, because we keep learning stuff and stuff that I find I never cease to be surprised. So what makes the McKenzie such a special river? Every river in its own way is special. Every river is different. They're all, they all take on characteristics of the landscapes they flow through. But with a couple of exceptions of other rivers around here. By here, I'm going to take a broad view of here to be kind of the central piece of the Cascade Mountains, extending, let's say, from the Canadian border down to south of Mount Lassen. Okay, that's when I talk about the Cascades. They actually go up into Canada and dribble out a little further south. But the Cascades are sort of a geographic feature that runs parallel to the coastline along the western edge of North America. And the McKenzie is a poster child, the poster child, I would argue, for a very unusual set of circumstances that I have not been able to find anywhere else in the world at the scale that it exists here. And I've looked. Doesn't mean it doesn't exist. Doesn't mean I haven't looked everywhere. But I've looked in a lot of places, and I can't find another place like it. There are parts of Japan that are a little like it, parts of Iceland. I have a feeling there are parts of Chile. But what is it that sets stage? What sets the stage is a couple of ingredients. You think of it as a recipe. The recipe here is, first, you have a range of volcanoes. The volcanoes are not here it's not a random thing that they're here. They're basically describing what happens when one of the plates of which the Earth is made, crust is a set of plates. The collision between two plates inevitably results in one of the plates going down, the other plate going up. And as the plate that is forced to go down gets deeper and deeper, it melts. And the pressure and the temperature of that melt and some of the chemistry that happens along the way result in a chain of volcanoes emerging at the surface. How many of you have heard this thing called the Ring of Fire? Okay, the Ring of Fire is this arc of volcanoes that pretty much encircles the entire Pacific, including Antarctica. And it's all the same story. That is, if you look at the Ring of Fire and you look at where the plate boundaries are happening, there's almost a one-to-one correspondence. So we've got a plate boundary happening about 100 miles offshore here. This is the plate boundary that's going to wake up again someday and create a lot of mischief for us. That we, I love geology, but I don't particularly want to live through a Cascadia megathrust earthquake, which we're overdue for. So, but I'm not going to talk about that. But one of the things that baked into that cake are the fact that we have a volcanic area that is set up on the continental side of that collision where the Pacific plate is going down over the North American plate. So that's why, here's something, if you point at a rock in the state of Oregon and you say, I think it's volcanic, you have about a 70% chance of being right anywhere you go. So that you can amuse your friends and neighbors. It's sort of like around here, if you pointed at a tree and say Douglas fir, you have about the same chance, which is good for me because I don't know my tree. But we're living in a very active volcanic area. So the story about the McKenzie is driven by this fact that we have a chain of mountains that are all of volcanic origin. And these mountains have been chugging away for quite some time. That is that roughly for the last, let's call it 50 million years, the plate has been doing what the plate's been doing offshore and has given us a landscape that is predominantly the consequence of volcanic eruption. And that is not just here in the McKenzie, but it's if you go to go to Eugene, there are volcanoes all around Eugene, old ones. If you go to the east of us, you can go, it's volcanic all the way out to the Ochocodes and beyond. So, this is like a big deal table that's being set geologically. But and volcanoes have certain characteristics, and I'll get into that just a bit. The other thing, though, is that along with the volcanoes, we have an enormous source of moisture nearby. It's raining on us. What's that source of moisture? The Pacific Ocean. The Pacific Ocean. And now, if it turned out we were in a part of the world where the wind went the other way, the Pacific could be sitting there just fine and dandy, but we wouldn't get the benefit of the moisture. What happens is that not only do we have a big, enormous reservoir of water, but we also are sitting at about 45 degrees latitude, and so we're in the path of the westerly winds. So the westerly winds pick up the moisture off the ocean and just slam it up against the edge of the continent. And of course, they slam it up against the mountains, and we get a lot of rain around here. Any idea how much rain we get around here, right here?
I'll say 75.
That's now here. This is a knowledgeable person. That's about right, and it goes up from here. And so Corvallis, Eugene get about 40, which incidentally is about the same as Washington D.C. But the problem is it all comes over, November to June 1st, and low intensity events, and then it turns off. But 75 inches is about right, and then if we go up to the top of the McKenzie Pass, any idea how much you get there? In a good wet year, you might get as much as 120 inches. Okay, picture that's 10 feet. The ceiling here, I'm guessing, is close to 10 feet. Dale, you've got it. I have shot my credibility. Ask a builder, and he'll. So picture on a good wet year at the top of the McKenzie Pass. 2 feet more than the size of this room in terms of rain falling down. That's a lot of rain and snow. It comes down as both rain and snow. A lot of snow at the high elevations. So you put together the water, the mountains, the precipitation, and then we add one more ingredient to it, which is that in the younger piece of it, I'm going to draw a distinction between the older volcanic landscape and the younger volcanic landscape. In the younger piece of the volcanic range, how many of you stood at the top of the McKenzie Pass at the Diorite Observatory? Everyone has, right? What do you see up there? Lots of lava, right? What does the lava look like? Is it a nice smooth surface, or is it grubbly, chunky, blocky bits of rock? That, right? Exactly. Imagine yourself a raindrop falling on, at the top of the Wright Observatory. Where do you go? You go down, because that rock, that lava, that young lava, is so fractured, so broken, that, and also so young, that the water, instead of running off laterally and finding its way into the creek, just goes down into the ground, and it goes deep. It goes wading. I'll come back to that in a second. But in contrast, here, what happens when it rains? Where does the water go? It goes right into to the nearest creek, right? This place is full of creeks, right? And the creeks lead to other bigger creeks, and eventually they all end up in the river. So already you're seeing this landscape is having these two different flavors. The young piece of it, a place where the water, instead of running off, it runs down. And in fact, you stand at the top of the Wright Observatory, and you can't point to a river or a creek or anything that's been eroded by water as far as the eye can see, at least until you get up onto the big mountains, the Three Sisters and so on. None of that ground has been moved an inch by water. All that water's come down. So 10 feet of water going straight down. All right. That's pretty unusual. There aren't many places where that goes on in a volcanic system. And then we move just to the west here, not far. How far are we from the crest of the Cascades? Probably 25 miles, somewhere there, 30 miles on that. We're in a completely different system. So the river has these different flavors depending on whether you're in that young piece of the Cascade. And by young, I don't mean like, yesterday from a human standpoint, but from a geological standpoint, there are lava flows. Some of the youngest lava flows in the state of Oregon are just up the road here. Anyone know which one it is? It's 1,500 years old. Came out of the Collier Cone, Three Sisters. Went down the White Branch Valley, okay, and it ended up on top of somewhat older flows that are about 12,000 years old. If we go up to Clear Lake, how many of you have been to Clear Lake? Everyone, right? Any idea what how old the flows are there? They're about 3,000, and they sort of feature into this story rather prominently. But so the point is, we're talking only thousands of years. There were people here. There were native people who saw these eruptions. This is thousands of years after Crater Lake exploded, and there were native people here as well. So this landscape has rocked and rolled and erupted dramatically over timescales that human beings have lived in. And it will do so again. I mean, that's part of the story around here. About 30 years ago, there was a story of talk of the bulge. Anyone remember the bulge? Yeah. The bulge was where there was a detection of the ground was inflating up Separation Creek. And everyone got very nervous, like maybe we're going to get an eruption, and then it kind of settled down a bit, but it's still raising, and nobody seems to know exactly what it all portends, but what it means is that at some point there'll be probably another eruption, and it'll probably be in that part of the Cascades. Anyway, so let me just stop there. So those are the big pieces of the story. I just want to make sure everyone's sort of on board with this story. Line of mountains, a lot of moisture, rain, broken rock that absorbs water. I mean, literally like the perfect sponge, geological sponge. And then to the west, where we're sitting here, a much older volcanic landscape. It also came out of volcanoes, but there's been enough time, roughly 30, 40, as much as 50 million years, for the landscape to transform itself from one where the water goes down to one where the water goes across the landscape. There's no storage, very little storage of water in this piece of the landscape. Does that make sense? I mean, again, if I had a picture of it, I'd be pointing at you, but I'm just trying to paint this picture in large terms. So, if those of you, how many of you are fishermen or women? How many of you fish? If you go to one of these creeks, like Lookout Creek, or Gate Creek, or Horse Creek, although Horse is a little different. At the end of the summer, is there much water there? No. In most places, you can kind of walk, barely get your knees wet, if you're good at hopping from rock to rock. However, has anybody noticed what the McKenzie looks like in September? Yeah. What does it look like? A whole lot of cold water, right?
Almost the same.
Almost the same. Exactly right. Exactly right. The variation in flow of the McKenzie is, barring a massive flood, is really modest by rivers. Yeah.
Yeah, I was just wondering, is it a binary between superporous and the opposite, or are there intermediate areas?
I love that you asked that question. It's a great question. Dale's question is.
Mike.
Oh, I'm sorry, Mike. Did I accuse you of being Dale? Oh, sorry. There he is. Mike.
I guess.
Sorry. I've now shot my credibility twice. That it's a great question, and it's actually the subject of very active research, because we are interested in what we call the phase shift, which is basically the shift that takes you from one condition to the other. And it is a continuum, and it looks like it takes about 1 million years.
That was my question.
About 500,000 to 1 million years. And we have really good evidence about how long it takes. And I can drink a bunch of these with a bunch of those details, but there's a lot of, for example, one of the things you can do, we have all kinds of cool tools now Like you can get digital maps of the landscape, right? And you can calculate, you can figure out where all the streams are, right? And you can add up the stream length for different areas. So we take areas in the High Cascades, the youngest piece of it, and we go to the oldest piece, and we do the same thing. We just add up the length of all the streams in these different regions. So, and we think of it as a function of age. And what happens is that it looks like you don't even get streams, for the most part, showing up for at least about 10,000 to 50,000 years. That is, the D. Wright Observatory is not, if everything just went on the way it is, it was going to take 10,000 years at least for rivers to begin to develop in that piece of the world. And to get a fully developed drainage system like we have in the Andrews or up on these hills, looks like it takes around 500,000 million years. Now, having said that, how many of you have ever walked up to Proxy Falls, up to 220? Beautiful hike. If you haven't done it, you should do it. It's a beautiful place. If you walk up to Proxy Falls, you will cross a stream that for much of the year is dry, but at this time of year, I bet if we walked up there, it would have water in it. And that stream is flowing on a lava flow that's only 1,500 years old. So here's a stream, what I just said is it takes 1 million years, or it's a couple tens of thousands to get a stream. Here's a stream that's only 1,500 years old. How did that happen? And what happens is that you can jumpstart this whole process of creating streams in the landscape if you basically coat the landscape with stuff. That's a geological term. And what kind of stuff are we talking about? We're talking about ash. We're talking about wind-blown material. We're talking about if we have a glacial lake up in the Three Sisters that breaks, which happens, used to happen a lot around here. You can coat the valley with mud, and under all of those circumstances, you basically block the access of the water from moving down, and it has to move across. Does that make sense? It turns out there are these weirdos that defy the main rule, but in general, it takes a long time for the High Cascade kind of place to turn into the Western Cascade. So what's happening is that the rivers in this landscape have depending on where they start, where they get their water, have these different flavors, really different flavors. So if we go to the High Cascades, one of the things that happen is the water that falls down, how much did you say it was?
10
About 10 feet, right. 10 feet, lots of water. Goes down, percolates down, it goes down on the order of about half to 3/4 of a mile down. I mean, it's a long way down. Not all, that's as deep as it usually gets. And eventually what will happen is it will find layers of lava. Remember what that High Cascade landscape is made of. It's made up of a series of lava flows, one on top of the other, like that. Think of each lava flow like an Oreo cookie, okay? How many of you eat? No, you don't have to answer. An Oreo cookie, right? Okay. What is an Oreo cookie? It's got, there's the crust, and then the good filling, right? That when you're a kid, you unscrew it. So think of it as that's basically what an individual lava flow looks like, and it's not really a stretch. What happens is the top and bottom are parts of the lava flow that, because they're in contact with cooler material, whether it's the air or the ground, tend to break apart and and create a lot of those holes and fractures that you see from the top of the McKenzie banks. The center cools more slowly, it's denser, and it resists breaking quite so much. So eventually, when you have 10 feet of water going down, it finds its way through all the broken crusts of the Oreo cookies, and eventually finds the layer of the creamy middle that doesn't let it move down any further, and then it moves sideways. Where does it go? Where does it end up? It's got to go somewhere.
It goes downhill.
Absolutely right. It goes downhill. And what it's doing, it's following the old lava flows, which are buried. It's following that center of that old lava flow that might be, 100,000 years old. It's been buried on top under all these other lava flows. Eventually, all that water has to go somewhere. And where does it come out? It comes out as springs. And the springs around here are some of the most incredible features I've seen anywhere in the world. And thank you. And interestingly enough, some of the most beautiful ones aren't even on the map. How many of you have seen the spring that's up Highway 242? It's called Lost Spring. And there's no sign. Forest Service politely filled up the parking area with large rocks so nobody can camp there anymore. Does anybody know what I'm talking about?
Yeah.
You know about that?
Went there for the first time last week.
You did?
Yeah.
Isn't that an amazing place?
Yeah.
We call that Hobbit Land. If you haven't seen this place, you go up 242, you go past Limberlost Campground. It's about, I'd say, 2.5, 3 miles beyond Limberlost. On the left, you'll know you're there.
Cabin,
What's that?
right after the cabin.
There's a cabin on the left side, and there's a parking area that you can park in. And then you have to sort of head towards the forest, away from the road. You'll find a trail, and you don't have to go very far. It's about 100 yards down the trail. You will be in like what we call Hobbit Land. I mean, it's this beautiful pond system. And it goes on for acres. We've tried to map this thing, and we can't map it. And it is the source of Lost Creek. That's where Lost Creek is.
That's the beginning of Lost
That's the
Creek.
beginning of Lost Creek. That's right. And that water, we have studied that water. We know all kinds of things about that water. That water took, on average, about 10 years between the time it was a raindrop and the time it showed up at the spring. And the springs there are very quiet little seeps. You have to sort of look for them, but they create this big lake environment. But it took 10 years for that water to follow its way down the hill. And we also know that that's the only spring that has any evidence of water that's being cooked up by the volcanoes themselves. When the volcanoes, when magma crystallizes underneath, it generates water. And we actually have a signal in that water, the chemistry of that water, that tells us that, hot magma is being cooked up under the rocks. So that's an amazing spring. But there are more. There is a spring up on Olali Creek. You know where Olali Campground is? Upstream of Olali. It's not on any map. You got to find the trail, and it's a funky trail. But to walk to this thing is amazing. And that one spring, I brought a guy out here from eWeb, and he said, if we could put a pipe right on that spring and send the water to Eugene, we could take care of Eugene's water needs in perpetuity. One spring. Okay? It just gushes out of the ground. But wait, there's more. How many of you been up to the spring at the top of Clear Lake? The Great Spring. Great Spring. Literally comes out of a lava flow. It looks like it almost comes out of a tree. And if you're in Clear Lake and you row your boat or your kayak up to the short end of the lake, you'll see a little river coming, you know, a mini river. If you go up that little river, this massive spring. So the point I'm trying to make is all that water, 10 feet of water, is coming out of these amazing springs. And it's for that reason that the main McKenzie the other one, the one everyone loves to love, is which, any guesses?
So it is.
Blue pool.
Blue pool.
Same thing. Water coming out of the base. It's always coming out of the base of these lava flows. In this case, it's pretty young lava flows. These lava flows have done other things too. They dammed the McKenzie River, creating Clear Lake. That was 3,000 years ago. With you paddle around, you see the 3,000-year-old forest still rooted in place on the floor, and it ran down. It dammed the McKenzie. It ran down the McKenzie, and what did it create along the way?
Waterfalls.
The waterfalls, exactly right. Coosa, Tamalich, and of course Sahaley Falls. Those are all individual flows that came down and stalled in the river valley, and then the river eventually found its way in on top of them. But 3,000 years is nothing to, there's almost no evidence in that whole section. If you do the waterfall hike, that goes around Sahaley and such, the rock, much of the rock there looks like it cooled yesterday. It's sharp. It has the same form that it did when it came out of the volcano 3,000 years ago. Let me just stop there and entertain more questions. Does that? I assume for some of you, you're not hearing this for the first time, or maybe there are pieces and so forth. But does it begin to? You begin to get a sense of the story and why this place is so unusual.
No.
A giant river that's spring-fed. Okay? Yeah, question?
So I'm curious, in your Oreo cookie description, do we know the depth of that center piece that if they've done drilling or whatever
Yeah.
research have they done? What do we know about that?
So picture that it's not just one Oreo cookie. You went to Costco and you bought a case of Oreo cookies.
Yeah.
And then you meticulously stack them one on top of the other.
Right.
All right, that's the way to picture it.
Yeah.
And as I say, it's probably, if you just look at the stack of Oreo cookies, it's probably at least 2 to 3 miles deep of Oreo cookies.
Wow.
And with each one Oreo cookie being an individual lava flow that came out at some point. Does that make sense?
Yeah, makes
Yeah.
total sense. So,
Go ahead.
but they vary in time. Obviously it's flows, and so the bottom ones are the oldest, and as they tier up, they're younger.
Bingo. Absolutely right. And as the bottom ones are also feeling the weight of all those other Oreo cookies on top, so they're getting really smushed, and they're losing a bunch of their identity as a consequence. So as you go up in the section, you're getting to younger and younger
So
explosions.
they're losing some of their porosity too?
I'm going to hand out PhDs at the end of this.
Just curious.
That's exactly right. The porosity decreases with depth, but you have to go about half a mile down before you do it. But, and here's something new. One of the things we're doing as sort of following this question of the phase shift, people have done all kinds of work here looking at the temperature profile. This is a big area for geothermal, right? Now hold that thought, because the possibility of down the road, the people have been eyeing this place for geothermal energy for a long time, particularly over by Newberry, but there was exploratory work done in the Three Sisters. There's a lot of conflict, as Val can help us understand, between wilderness areas and geothermal development. But that aside, one of the things that people have done is drilled big holes, lowered thermometers, And what the thermometers reveal is that if you go down to the youngest part, if you're looking at rocks that have some of the youngest section, the youngest part of the high cascade, what do you think the temperature profile? This is a hard, you get 2 PhDs if you get this question. What do you think the profile of temperature would be? We're going to go down, let's say we go down half a mile. So we drop our thermometer into this hole, it goes down, down, down. What do you think the temperature looks like as it drops down?
Did when it cool?
It's hot.
Well, hotter, cooler, yeah. What it does is something very interesting.
It's hot and cool.
It stays.
I want those 2 PhDs.
No, you don't. What happens is you stay at more or less the same temperature for about the first half of that half mile. Now, why is that?
What temperature is that?
Well, it's kind of a reasonable temperature. It varies depending on where the elevation is, but it's sort of on the order of about 30 to 40 degrees Fahrenheit. That's kind of the average temperature around here. So what's happening is that first half mile or so, it has the temperature of the surface. Why would you think that would be true?
Because the water is boiling.
All right, sir, you at least got a master. The water, that's exactly right. The water is bringing that temperature down, and it's only when you get to depth that you start getting heat from the stuff that's being cooked up from underneath. And we actually have a term for this called the rain curtain effect. And there are not many places that have rain curtains like this. So, and this is new stuff. Let me throw another bit out here because there's a piece of all this. I mean, all of this is incredible gee whiz, right? I mean, we've got the springs, we've got these rivers that don't flood. The McKenzie is very flood challenged. Here, less so downstream. You go down below the South Fork, and suddenly you're in flood territory. It's fair to have a cabin sitting on the banks of the river here because the chance of a flood, it's not zero, but this is mostly spring. Think of it like a big spring river. You go down further, you would not want a house on the banks of the river. I mean, you run a real risk. So, because as you get from the part of the landscape where you're being fed by this big volcanic system, by that 10 feet of water that's coming out of springs, that's all modulated.
Very constant.
Very constant. It goes up and down, but the range over which it goes up and down is really small. That's where our water comes from in the summer.
And it's all getting stored in the lot.
And it's being stored in the lot.
Lower down.
Lower down, you've lost the
So between, you have all the streams feeding in. Surface, you go up and down.
Right, but there aren't that many streams doing that up here because it's just all spring-fed streams. So you get down below, you've got all those streams that are being fed by the landscape where all that porosity has gone away because of time and weathering and breakdown of the lava and so forth. And there it's like water off the duck's back. And that's where our floods come from. Our floods come from this landscape and further downstream. And this is true, not just here, it's all the way to the whole Willamette system. In the summertime, if you were to take the dams off the system, about 30% of the flow into Portland Harbor in late summer is the McKenzie River. The Willamette is the McKenzie River in the summer. And which is, I mean, who knew, right? But in the wintertime, it's not that the McKenzie turns off, but the other parts of the landscape light up, wet up. And so the floods happen when we get classically rain on snow events in this lower, older piece of landscape. So is this making sense that there's this two-tone landscape that's being driven by the basic geology, fed by this water, and I obviously can go on and on about this, but let me just leave you with something that I think is one of the most important things to reflect on. This is really unusual, and it's unusual at the global scale, and it's particularly unusual at the scale of the Western United States. So we all know the climate is changing in different ways, in different places, and a lot of that is because, a big piece of it is things are warming up. We're losing snowpack. How is this going to play out here versus other places? It's a complicated thing to wrap your mind around because two things are happening. One is we're losing snow here, just like the Sierras are. The Rockies a little less so because the snow is colder there, so even when it warms up, still maintain snowpack. But the Cascade system is incredibly vulnerable to snow loss because basically it's kind of warm here in the winter. It doesn't feel warm necessarily, but a lot of our snow comes down at about 31, 32 degrees, right close to the transition. You bump that a couple clicks up in the temperature, and suddenly you're in rain. You lose the snow. And everyone who's lived here, I think, will know this place used to get, like, every winter, right? I see some head nods. How many times a winter would you at least have to worry about putting on chains around here?
A lot.
A lot.
Yeah.
The Andrews, we'd get snow multiple times, and then it would melt, right? It would be around for a couple days, and then you'd get a rain on top of it, or it would warm up a bit, and the snow would go away, but then it would happen again. That transition, which used to be around 1,500 feet, is probably more like 2,000, 2,500, somewhere in that neck of the woods. So we're losing snow, but we're not losing geology. And so that sponge system, that lava sponge, isn't going anywhere. At least not at timescales that matter to us. And what that means is we've got a built-in reservoir that nobody else has in the whole Western U.S. And I am deeply convinced that down the road, the rivers that have this property, that they drain this young real estate, this young volcanic landscape. It's not just the McKenzie. It's the McKenzie, it's the Deschutes, it's the North Umpqua, but not the South Umpqua. It's the Clackamas, some of it. It's the Rogue, some of it. It's the Klamath, some of it. And then the poster child in California is actually the Pitt River. Have you ever heard of the Pitt River? Most of the Sacramento flow in the summertime comes out of the Pitt River. And the Pitt River comes out of Lassen, and Lassen's has the same story.
What about McLeod?
The McLeod also, the McLeod, but I think McLeod,
It's very dry recently. Very low.
The McLeod, I think, gets a lot of its water off Shasta, as I recall. And so we're talking about, we're losing glaciers, and so we're going to lose glacier melt as a, the McLeod is a little bit different. The Fall River.
That explains it.
Yeah.
So you just brought up something that I wanted to ask about, because everything that you've described, about this reservoir, I don't know, but I'm really concerned within my lifetime, the receding glaciers in the Three Sisters. But is there any connection, between the hydrology of the receding glaciers, which I think in my lifetime may disappear, in that hydrology of what's going to go down?
It's not a big deal.
Okay.
Where it's a big deal the Andes or the Himalayas. There, people are really concerned because most of the summer water comes from melting glaciers. A place around here where it is a big deal is on Mount Hood. Like most of the Apple Country, the Hood River Valley, that is glacial, but it's sandy the same. The big volcanoes are different than this lava story. They're actually not basaltic lava. They're a different kind of lava. They're andesite, and they don't do the same. They don't. The lava is stickier. It has more silica in it, and so it builds these instead of flowing down like water. The big, mountains that we all know in the Cascades, those do not. They have much less of this property that we're talking about. That's where the glaciers are. So the glaciers are the storage on those big mountains. But that's not what's really driving things like the McKenzie. So we could lose glaciers here. My feeling is that the McKenzie is going to be, I don't know what the time scale is. I don't know, because it depends on the climate. It could be 30 years, it could be 50, it could be 100. It could be my grandson's children's life. I don't know. But I believe that the Pacific Northwest, and particularly this part of it, is going to be seen as essentially the water tower of the Western U.S. And and the interesting thing is, I don't aspire to the role of prophet in the wilderness, waving the
Right.
the sky is falling. That's not my gig. But I really think we should be thinking about it pretty hard. Yeah.
So I live up on Highway 242, and talking to the Yales, who I bought my property from, in the last century up until the 1950s, the names of Lost Creek and White Branch describe what happened in the spring. White Branch flowed white, and I don't know if that was caused by glacier melt or a deposit.
Yeah. Your local streams, Lost and White Branch, are two of the goofiest streams on the whole planet. And that's a geological term, and you could write it down and put it in your paper. Goofy.
That's why I live there.
No, people have actually written PhD dissertations about the White Branch system.
Yeah.
The white of White Branch, so they're Lost Creek, which the long stream is White Branch. It goes all the way up to Collier Glacier, and there is Collier Lake up there, and Collier Cone. Collier Cone last erupted, as I say, about 1,500 years ago. And basically it erupted and sort of dammed off the water that was being fed off of the Collier Glacier. And so, in fact, it was a giant whirlpool. It was like a toilet bowl up there. Things just went down and nobody knows where they came out. But that's the source of White Branch. So at the very heart of the Three Sisters on the west side is where water is being fed into White Branch. And it used to be a lot of glacial flour, so it was white. There have also been a series of breakout floods up there, including one not too long ago that ran down the White Branch Valley. So that's White Branch. But White Branch, as you know, goes away in the summertime, right? It disappears. It's gone. Lost is being fed by water that's coming probably all the way down the crest. It's following a lava flow from Sims Butte that's about 13,000 years old, and then on top of it is the Collier Creek flow as well. And in fact, where the spring is, if you go there, what you're seeing is that's the end of the Sims, the 13,000-year-old flow, sort of stops there, and that's why the water's coming right there. Does that make some sense?
Yes, so it does.
It's a very unusual system. Yeah, if you think of, remember nothing from this talk except the words unusual and goofy. You'll have the basic story. Other questions? Yeah.
You had mentioned being able to find like some sort of a mineral signature about water that's going down, hitting the magma, coming back up. And then you'd mentioned timelines about when the water goes into the, and how it comes out. How did you figure out, how did they figure out the timing?
That's a great, these are really good questions. There are two different things. One is the chemistry. You use to figure out where the water is being sourced, whether it's coming out of the atmosphere, it's being generated by magmatic processes. You use an isotope of hydrogen called tritium, and so most of the springs around here only have atmospheric concentrations, but that one has magmatic concentration. But tritium turns out to be a very interesting thing. Tritium is one of the isotopes that was generated by the bombs, by the atomic bombs, hydrogen bombs. And so what happened is in the early 50s, because there was all this above ground hydrogen bomb testing in the South Pacific, but other places too, the atmosphere got dosed with radioactive isotopes. I remember this as a kid, there was something about you're not supposed to drink milk because it turns out calcium concentrates some of these isotopes. Anyways, we stopped exploding bombs in the atmosphere. So all of that has been decaying. All that tritium that went into the atmosphere has decayed. And the rate at which it's decaying is known.
The half-life.
The half-life, exactly. Sort of how quickly, and it's on order of 30 years or something like that. I can't remember the details. Okay, so you with me so far? So when rain falls, it takes a snapshot of the concentration of tritium that's in the atmosphere at the time it falls, right? But literally like a snapshot. And then it goes in the ground. And then it mixes with whatever else is in there. And every other drop has also taken that same snapshot of the atmosphere. So if you get a glass of water coming out of the spring and you measure the tritium concentration in that water, and you know how long you can come up with an average, it's just an average, of how long that water's been. Does that make sense? That's how we do it. And I'm making it sound easy, it's not. You know, my smarter graduates had to do it. I didn't know how to do it. But it's a great question. Basically there are markers, time markers that you can kind of use to figure some of this stuff out.
And then on average, 10 years or so.
It's between 7 and 10 years. Some of them, how many of you seen the Metolius Spring on the that one's a little older. That's about 20 years, 20, 25 years. So, so I mean, just picture that. That means that water that whatever was happening 25. Remember the millennium where everything was going to, Y2K, right?
Yes.
Y2K, right? Okay, so that was happening when the water that's now coming out of the Metolius Spring was coming down. That's kind of a cool thing. Yeah.
So for that water that's purely geological, is that just a trivial measurable amount, or does it enter into water flow questions?
It's a trivial, from the standpoint of water production, it's a trivial amount, but it has a distinctive chemical flavor. One of the things, so let me just punctuate this with something that even my wife, who has listened patiently to no end of these sort of diatribes, doesn't know. One of the things you can do, one of the fun games you can do with numbers, is you can take all right, so there's 10 feet of water, and let's say it's 7 years worth of water So if the age is 7 years, where we get it from the spring, basically we know that there's 7 years worth of active water in that, coming out of that spring, right? You know, it's measuring at least 7 years of water. And what did we say? It's 10 feet times 7 years, so that's 70 feet of water that's in play. And then you multiply that by the area that's under consideration, and you end up with a volume, the total volume of water. We think that in the McKenzie, I'm going to give it to you, I have to do some, I'm going to give it in cubic kilometers, which is because I think in that, but it's, what's the conversion? It's about 3, a factor of 3, roughly. Okay, so
I'm not so good.
So we think in the McKenzie, it's about 1 cubic mile of water is being stored just in the McKenzie Basin. A cubic mile. Picture that. A mile by a mile by a mile. That's a cubic mile of water that's in active. There's probably a lot more that's not in active status, but a cubic mile. But we have recently, in work being done by my colleagues at the University of Oregon, we were coming up with numbers previously that said that we think for the whole Cascade system, we're talking about 10 cubic miles of water, which, to put it in perspective, that's about the same amount of water as you'll find in Lake Mead in Arizona. When it's full, which ain't happening anytime soon. Or Lake Geneva. Lake Geneva. It's more than what was in Salt Lake, and it isn't salty. It's beautiful fresh water. We now think that estimate is a gross underestimate. We think it's now closer to 20, if not more, 30 cubic miles of water. There's nowhere else on the planet that I know of that has that much water stored in the mountains, that is at an elevation where it has the potential to run down into somebody's city or pipe or something. I don't know of any other place. This is a unique place. It's an important place from all kinds of standpoints. And I hope we haven't talked about fish or people's livelihoods or, you know, just the beauty. I mean, there are so many dimensions to why it's important. But just on the basic story of the geology alone, it's a hugely important piece of real estate. And so, you know, Angel, you know, I think there's a future in selling beer up here because you know, spring beer. That's right. We need. Trust me, Nestle knows. The Nestle people know what's going on, and I'm going to put a plug in. Val will appreciate this. There have been big fights where these spring systems have been on private land, you know, because the springs really feed the big river systems. Here, they're almost, the big ones are all on public land. They're all land managed by the U.S. Forest Service. So that has a lot to say about how this place is going to, you know, what the future is going to be. The spring system, the water production system is on federal land. But that's only an agreement. You know, I have no idea what would happen in a 10th year of drought. Well, what I think all kinds of things can happen out of this. I think we can be thinking about moving water around. There's always been the big, we're going to move the Columbia River, California. I mean, that isn't going to happen anytime soon. But until we get really cheap energy that lets us do desalinization at a big scale, this place is going to just be enormously valuable just for the water.
So,
Yeah.
so I know in geological time, it's like a nanosecond, but do we have, we have any concept about how, because we have the variation, with 10, 15 years, and snowpack and rain and the whole bit, as to how much that volume is changing in very short periods of time in that reservoir that's sitting there?
I'm not just making this, these are really, really good questions. And you're speaking directly to something that the answer is we don't know. We don't know what would happen. How many of you remember, what was it? It was the year 2014. Remember the year we didn't have any snow? The no snow year.
I biked all the way to D. Wright.
Yeah.
In the middle of the winter.
Yeah.
All the way to D. Wright.
Yep. There was no
Middle
snow.
of the winter.
Yeah. And people pointed to that and said, this is what the year 2080 will look like. I think grossly optimistic. I mean, I think it'll be the year 2050. There will be, we will have runs of years without snow. Here. And all the work that's been done in the McKenzie shows that very clearly. Do not invest in low elevation ski resorts. It's going to go away. We don't know what the consequences are, not just of a single dry year, but of a run of dry years. And there are techniques, fancy, sophisticated techniques involving helicopters and instruments that give you a window into the subsurface. This is a bunch of what I've been talking about. One of the things that's so challenging about it is you can't see it. A spring is like a window. A drill hole is like a little window, but it's at completely the wrong scale. You're asking the question, which we're also asking, which is, what's the whole landscape going to do? The answer is we don't know. We really don't know. But if I ran the circus, I would say this is worth knowing. And it would require an investment, not huge by a lot of standards, but to do a decent survey that would begin to give us a sense of the scale of the aquifer, where the water is stored, and how it changes over time. It's every time you do that, it's probably $250,000. It's not cheap, but given if you drink the Kool-Aid I've been selling today, this is pretty fundamental. It's pretty fundamental to what's going to happen. So I would love to see an investment that, I'm working with people who do this like in Hawaii or in Yellowstone, where they fly these instruments around and it's imperfect. I mean, it's not like you get this picture of this like giant lake in a little boat floating in it. And don't picture it. It's all fractures and rock. The pictures are very pretty, multicolored, but you have to know how to look at them. But I think this is something we should be attending. I think it's not just because I like science. I mean, I think this is an important bit of business. Yeah. It's a great question, really good question. Any other questions? I've sort of taken more of your time, and it's dinner time. Yeah.
How much of the water, how much of the 10 feet of water do you think heads east side of the Cascades?
I'm so happy. A lot. There is a lot of water that goes under the crest of the Cascades. We think for the upper part of the McKenzie that up to 30% of some of those basins may show up in the Mattolas.
Can we charge Ben for that?
There you go.
Yeah, they're overdrawing their aquifer.
It's a really good question, because in this landscape you can't trust topography to tell you which way the water goes. Everyone says, well, water goes downhill. Well, yeah, it does, but you don't know. You don't know whether it's not necessarily following what's on the surface. It's following these layers that are subsurface. The Deschutes is the kissing cousin of the McKenzie. Deschutes has the same story going on, and in fact, my interest in the McKenzie really blossomed because I was working.
What feeds the Deschutes?
Staying there too.
What's that?
South Springs.
Big Springs, the same story, although it's different. The Deschutes gets a lot less water than we do on this side. You know, I mean, that rainfall gradient you hit, I mean, you go from 100 inches to 20 inches over the course of 6 miles or something like that. I mean, it's amazing, the gradient. So you get less water. The lava flows that it looks like, the lava flows are more sort of kind of regional. And one of the things, you can see this thing for yourself. You've all driven to Redmond, right? Or Bend. Same thing. Okay, you cross the Deschutes River, right? It's a little tiny thing, right? A couple of these picnic tables would span it. And originally I thought it was all because of irrigation diversions, which is a piece of the story. But then you go down to Warm Springs, which is about 60 miles, 70 miles north, somewhere there. It's a massive river. And all that water that has come off the Cascades is, including coming out of the Metolian system, and it's all filled. I mean, it's a huge river at that point, and that's all.
The Crooked River flowing into it too.
You got the Crooked, but the Crooked doesn't. Well, the Crooked's weird because there's actually water that comes off the Cascades, goes under the Deschutes, and reappears in the Crooked. Yes, it's like a train cross, you know, like a train system. Isn't that bizarre?
That's amazing.
Is it not? This is a very unusual place that we live in.
Sad Oreo
No
cookie.
wonder it's crooked.
Right? Exactly. Any other questions? I really enjoy these questions.
Might
Yeah.
be a little off topic, but there's a spring over west of Madras that a lot of Madras gets its water from. I think it's called Crystal Springs.
I'm not.
You heard of that?
It doesn't surprise me. But yeah.
There's a little trout fishing there. I think it's right.
It's not Warm Springs. I mean, Warm Springs is what it sounds like.
Yeah, I don't think
Crystal
so. There's
Springs.
actually, I know a bunch of the water goes to the town of
Yeah.
Madras, what they said. But somebody told me the water coming out of that spring is 100 years old. Is that
But
possible?
it is possible. I mean, it is entirely possible. And I've been, waving this flag. Oh my God, the river's 7 years old, 10 years old, 20 years old. If you're in Nebraska and you're pumping the Ogallala Aquifer, that water's 20,000 years old. What distinguishes this water here is actually that it's being actively recharged. So it's not like we're pumping it dry. That's a really important. That's part of the story about why we're going to have water when Central Valley of California. Incidentally, California, what's going on there? The water that, as I was saying, that the water that comes off of like the Pitt River area, the Lassen area, and so forth, that's Sacramento. They're taking that water, and it comes down to Sacramento, and it goes into something called the Trans-Bay Diversion Canal, and they basically take that water, wrap it around the bay, and then run it up the San Joaquin River to water the rice and the almonds. So I mean, people do crazy things with water. I mean, and it's heavy, and it's energy intensive, and all these things sort of kick in. Any other questions? I'm really.
You mentioned the temperature.
Yeah.
So there's hot springs sprinkled around up here. What makes those happen? Is that just luck of the draw?
No. What you're doing, by the way, these questions are all filling in the gaps that I would have otherwise walked out the door. Why didn't I find No, what's happening? So there are a bunch of hot springs here. There's the one right by the McKenzie, right? Belknap. Cougar.
Deer Creek.
Deer Creek, right. Okay, so what's going on there? So what's going on there is that the river systems here, the basic structure of the landscape here is controlled by some big faults. Like, in fact, you know, I've given you this whole broad view of, you know, the high Cascades over here and the Western Cascade. One of the reasons why it's so easy to see this contrast in this landscape is that there is an offset that's created by a fault, a place where the Earth's crust has moved relative to itself. So when you drive up the McKenzie, and when you drive up from here, you're driving what direction? You're driving due east, right? But then what happens? You turn north. Where you turn north is more or less right at Belknap, right? Pretty close to the big curve there. At that point, you pick up a fault, which is the whole, it's called the Horse Creek Fault. And the upper river is following that fault system. And then it breaches, more or less, it breaches the fault. And the fault has the somewhat paradoxically, let me do it relative to you, so I can think about it. If this is the Western Cascades, it is up relative to the high Cascades. So Carpenter Mountain here is a piece of that fault. If you go up to the top of Carpenter Mountain, right above us, right where we're standing, you will be looking straight at the high Cascades. You'll be seeing a beautiful view of the three systems, right? Have you done this? If you haven't, it's really worth it. They have a look out up there and so forth. Okay, what you're standing on the fault. This piece of real estate here is part of that fault. So what happens then is that because of this fault, water that's coming down and coming deep through that lava pile. A lot of it's going to these cold springs, but at least some of it is going very deep. But it encounters that fault and it's pushed up because it can't get, it's impermeable right there. And that's where Deer Creek is. There's another fault at Cougar. There's another fault at the Belknap Spring Complex. It's the same as the Deer Creek. It's all being forced by the fault. So basically what's happening, these hot springs, is that some fraction of that water is going down deep. It's not running, it's probably following broken lava flows, just like the rest, but it's finding its way deep and then flowing along these lava flows, and then it hits one of these faults and it bounces back up again, and we get a hot spring. Does that make sense? That's what it is. Yeah.
So when we talk about the aquifer being 1 square mile or 10 square miles, and I'm imagining in my
Cubic.
Am I looking at a pool, or am I looking for a big area of fractured lava flows? And if we have a 10-year drought, the pressure that maintained that area, will those walls start to collapse?
All right, a couple things. It's cubic miles, not square.
Okay.
The second is there is no lake.
Okay.
There is nothing. So whatever it's all about fractures. It's all about fractures. The third thing is that it's unlikely that the system is being held together necessarily by water pressure. However, the pressure in this system is really an important piece of it, because what is happening here, I went around for a couple of years, in retrospect, talking like an idiot, which, you know, as some people in the audience will know, is not an uncommon practice of mine. But I had this notion that, well, don't worry, be happy. If it comes down as rain or it comes down as snow, it's still going to go in the ground, and it's like having a big reservoir. There's a twist to the story. The story is that the water that comes out is in springs, is being fed by pressure. And water in is water out. All of you have had this experience of the garden hose lying on the garage, on your driveway in the sun, right? You turn the water on, you instantly get water out. But what temperature is it? It's hot because it's the water that's in the hose. It's being pushed out by the pressure of the new water that you're getting into the system, right? You all know that? The same thing is going on here. So water into this, so if we don't have water coming in, it sort of gets at your question, but the question is, how vulnerable is the system if the input of water diminishes? And in the current thinking is that we're not going to see a big change in precip around here. It's going to get hotter, but the amount of water is going to stay. That's the thinking, and there are different models tell you different pieces of that story. You know, that's not something you can take to the bank, but it's, you know, it's a first approximation. But if the timing of water shifts, because we don't, you know, it all comes in as rain in the winter. We don't get the snowmelt peak, so we don't have that pressure component. Are you with me on this? Then we still have a decrease because we lose that pressure. And in this case, and this is a really hard thing to communicate, but because we have so much water stored in the ground, if you change the timing of when that pressure pulse occurs, because you lose your snow, now it all comes in January and February and March, and you don't have the April and May snowmelt that you once did. Now you start that curve of losing water. Instead of starting it in June, May or June, you start it in February or March. You with me so far?
Yeah.
Okay. So now you have to slide. You get to slide down that curve further, because by the time you have to, because our rain turns off in the summertime here, you have to wait till the fall. So suddenly the timing, the amount of time between when the last input happens and when you get the next rain that sort of wets things up again, that time becomes longer. And over that time, it's like your bathtub is draining longer. Does that make sense? It's a hard thing to get your mind around. So, because what it doesn't deny what I just said before, which is we're going to have water when no one else does, but we are also vulnerable to lose some of that water. And that's the big unknown. That is the single biggest unknown we have here, is we don't know how that's going to play out. And I don't know. I mean, I thought when we had the year with no snow that we would see all-time record low flows on the McKenzie, and we did not. It sort of tied the record, but it didn't go any lower. I would have bet that it went lower. But I don't know what would happen if we had 2, 3, 4, 5, 10 years in a row of
Which is well within the possibility.
absolutely true. Absolutely. That is the big unknown. That's the single biggest unknown, and it's worth thinking about, because we will be vulnerable to that even as we have water and no one else does. Both those things are true. Does that make sense? I mean, it's and I have been unable to convince the Oregon Department of Water Resources that they ought to be thinking along these lines, because I think it's a big deal. Potentially hasn't shown up yet. Any other final questions before we go on with our lives? Thank you very much. It's been really.